A model rocket is fired vertically upwards using a catapult from the top of a hill. The hill is 100 meters high. The rocket crashes on the ground 35 seconds after it was launched. Air resistance is negligible. Calculate the value and the direction of the rocket's acceleration 3 seconds after launch. The velocity of the rocket when it reaches its highest point. The velocity of the rocket when it was launched. And the height above the top of the hill the rocket travels. In this example, it is given that the rocket crashes on the ground 100 meters below its starting point, 35 seconds after it was launched. Since the air resistance is negligible, the rocket has a constant downward acceleration of 9.8 meters per second squared at all time. Therefore, the acceleration of the rocket 3 seconds after it was launched is 9.8 meters per second squared downwards. At the maximum height, the velocity is 0. Next we calculate the initial velocity of the rocket when it was launched. We use a constant acceleration equation, y2, which denotes the final position, minus y0, the initial position, is equal to the initial velocity times time, plus half times the constant acceleration times time squared. Rearranging the above equation, we get the equation for the initial velocity equals to, the difference between final and initial position over time, minus half times the acceleration times time. Substituting the values, we get that the initial velocity is equal to 168.64 meters per second. To calculate the height above the top of the hill that the rocket traveled, we use the constant acceleration equation that does not involve time, because time is unknown. The position above the starting point is equal to the velocity at the highest point squared, minus the initial velocity squared, divided by 2 times the acceleration. Substituting the values of the velocity at the highest point as 0. The previously calculated initial velocity as 168.64 meters per second. And the acceleration as negative 9.8 meters per second square. We get that the distance above the starting point that the rocket traveled is 1450.99 meters. We can plot a position versus time graph using the equation, y, minus y0, equals to the initial velocity, plus half, times the acceleration, times time squared. From the graph shown, notice that at time 0, the rocket's position is equal to 0 meter. At time 17.21 seconds, the rocket reached its highest elevation of 1450.99 meter above the top of the hill. And at 35 seconds, the rocket crashes at altitude negative 100 meter. The escape hatch on a rocket ship is designed to drop to the ground when it is opened. During testing, when the rocket ship is standing on the Earth, it took 0.5 seconds for the hatch to reach the ground. The rocket ship lands on the Moon, the escape hatch is opened and allowed to fall off, and it takes 1.225 seconds to reach the ground. Calculate the acceleration due to the gravity on the Moon. Let the letter h be the common height of the escape hatch. Given that the initial velocity is 0 because the escape hatch will be at rest before being opened. The time taken on Earth is 0.5 seconds. And the time taken on the Moon is 1.225 seconds. We use a constant acceleration equation that involves time and displacement to solve this problem. Substituting the initial velocity as 0, reduced the above equation to h equals to half times acceleration times time squared. Let the letter g be the acceleration due to gravity on the Earth. And the letter g with subscript m to be the acceleration due to gravity on the Moon. Using the values on the Earth, h is calculated to be 1.225 meter. Since the height on the Moon is the same with the height on the Earth, we use the same h value to calculate the acceleration due to gravity on the Moon. We solved for the acceleration due to gravity on the Moon to be 1.63 meter per second squared. A boat and a submarine are traveling in the same direction. The boat is traveling at 6.7 meter per second with a constant acceleration of 1 meter per second squared. While the submarine was at rest and started to move with a constant acceleration of 2 meter per second squared. The submarine overtakes the boat 6 seconds after starting to move. What is the distance between the submarine's starting point and their meeting point? At what time will they meet again after the 6 seconds? It is given that the boat's initial velocity is 6.7 meter per second, and its acceleration is 1 meter per second squared. While the submarine's initial velocity is 0 and acceleration is 2 meter per second squared. The submarine overtakes the boat 6 seconds after starting to move. To calculate the distance the submarine traveled by the same it meets up with the boat, we use the equation of distance equals to the initial velocity of the submarine times t, plus 0.5 times the acceleration times t squared. Substituting the value of the initial velocity as 0. The acceleration as 2 meter per second squared. And the time as 6 seconds. We obtained that the distance the submarine traveled is 36 meters. It is given that the boat's initial velocity is 6.7 meter per second, and its acceleration is 1 meter per second squared. While the submarine's initial velocity is 0 and acceleration is 2 meter per second squared. The submarine overtakes the boat 6 seconds after starting to move. To find out what time will they meet again after 6 seconds, we first have to determine how far away was the initial distance of the boat and the submarine, since the boat was moving before the submarine started to move. Assume that the boat was behind the submarine. The distance of the submarine plus the initial distance between them is equal to the displacement of the boat. Using the equation of displacement, equals to the initial velocity times t, plus 0.5 times the acceleration times t squared. Since the initial velocity of the submarine is 0, we just use 0.5 times the acceleration times t squared for its displacement. Substituting the acceleration of the submarine as 2. The initial velocity of the boat is 6.7. The acceleration of the boat is 1. And the time is 6. We get that the submarine was 22.2 meter ahead of the boat. After calculating the initial distance between the submarine and the boat, we can now find the time that they meet using the same equation. Plug in the initial distance value of 22.2. We get a quadratic equation of 0.5 times t squared, minus 6.7 times t, plus 22.2, equals to 0. Solving the quadratic equation, we get that at time 6 seconds and 7.4 seconds, the submarine and the boat meet. We can calculate one variable from another variable in more than one way. Either directly, shown here by the red path, or indirectly, shown here by the purple path. And the direct and indirect ways are always equivalent. So for example, if we are given the instantaneous velocity, and want to find the average velocity, we can either calculate the average velocity directly using the direct relation, or we can calculate the instantaneous position, then use it to calculate the average velocity. Both ways are equivalent and lead to the same answer. This is what we mean by self-consistency. Here's a strategy for solving 1D kinematic problems. First, don't panic. Relax. Take a few deep breaths. It's probably not as hard as it initially looks. 3. Decide whether or not this is a 1D kinematics problem. In a 1D kinematics problem, a point that represents an object is moving along a linear path, such that only one coordinate can be used to define the position of the object. 4. List all the information that you are given, including the time history equations, and the initial conditions. For example, you may be given the acceleration as a function of time, a of t equals 10t minus t squared, and some initial conditions, such as, at time 0, v is equal to 5, and that at time 0, x is equal to 0. 5. List all the quantities that you are asked to calculate. For example, you may be asked to derive the equation for x as a function of time. 6. Recall the diagram that relates the different quantities. 7. Find the most direct way to calculate the required quantities from the input quantities. Finally, do the actual calculations, by following the path in the diagram.